To simplify our understanding of the conversion from analog to digital signals, we'll start from the simplest periodic analog signal, the humble sine wave. We had previously derived the sine function, and it's represented by this equation. The equation is not really important in this context, but what is important is that the sine wave is in a sense a one-dimensional function. Though I may have represented the sine wave as a squiggly shape on a two-dimensional plane, it's actually a single valued spatial point at any given time, if you don't consider time as a dimension, of course. As you progress time, we can imagine that the sine wave acquires a different value. How many unique values can it have? Infinitely many, of course. The sine wave is said to be a continuous function over time, meaning that no matter how close two time intervals are, you wouldn't be able to find a single break in the signal, nor a loss of resolution, nor staggering of the shape of the wave function. The signal is continuous. A clear advantage of digital signals over analog signals is in its storage capabilities. How then are we supposed to store a signal which has infinitely many points? All the hard drives in the world could not accommodate the number of unique and distinct signal values that this one sine function can produce. Obviously, for sanity's sake, we wouldn't want to store all these values, only enough values to closely resemble the wave function. So what we want to do is to break apart the wave to make it discontinuous, to provide values only at certain points in time, to convert it into a discrete signal. The process of transforming an analog signal to a digital one begins here, by asking the question, how often do we want to measure the signal? Or how many samples do we want to have within a given interval of time? In this example, we have 30 samples within a 1 second interval of this 1 Hz sine wave. We can also say that we have sampled this wave every 0.03 seconds. This seems like a fairly accurate representation of the sine wave, right? We can also go lower by sampling it 20 times a second, or 8, or even 2. Or go higher and sample it 44,100 times a second. What's the right number? How many samples are enough to accurately represent this wave then? Well, thankfully, it's not as arbitrary as you think. Continuous to discrete signal conversion is governed by the Nyquist Shannon Sampling Theorem, which states that any band-limited continuous time signal can be accurately converted to and from digital signals when sampled at a rate at least twice as high as the highest frequency component of the waveform. Sounds complicated, but let's break it down. The sampling theorem states two important facts. One, that to represent an analog signal in the digital domain, the number of samples we would need for each second of the signal should be more than the highest frequency represented by the signal. If a signal has a 10 kHz frequency component, the sampling rate needs to be more than 20 kHz. It also states that the analog signal needs to be band limited to the highest frequency and cannot contain any frequencies above that. Let's put a pin on the second point and just talk about the first. In our case, we had a 1 Hz sine wave. This is a constant 1 Hz wave, and 1 Hz is the highest frequency that this wave function will ever produce. The sampling theorem states that to digitally represent this wave, we need at least more than 2 samples. Let's say 3. Any more is fine as well, but the minimum required is 3. We can say that the sample rate is 3 Hz. Hertz is an overloaded term here, and not to be confused with the frequency aspect of the wave. The reason that both cycles per second, which is the frequency, and samples per second, which is the sample rate, have the same derived unit of Hertz is because they both represent the same basic unit of 1/seconds. This is how a 1 Hz wave could be sampled using 3 sample points. You might wonder at this point that 3 points are clearly not enough to represent this wave correctly without losing a lot of resolution. I mean, if this sample waveform would have to be converted back into the analog signal, there is room for interpretation, right? The signal could be rendered in several different ways. Surely, if the 1 Hz wave were to be sampled at, say, 40 Hz sampling rate, there would be less room for divergence, and you'd get a more accurate representation, right? Well, the short answer is no. This is where a lot of misconceptions of higher sampling rate equal to better audio comes from. The absolute beauty of the sampling theorem is that it proves mathematically that both 3 Hz sample waveform and 40 Hz sample waveform of a 1 Hz wave, when reconverted back into its analog form, doesn't just produce the same output signal, but produces a signal which is indistinguishable from the original analog input signal before conversion. The input and output signals would essentially be carbon copies of each other with no loss in resolution. This seems really strange and unintuitive, because you're essentially stripping out information and discarding it when converting it into a digital signal, and then when you reconvert it back, how is this missing information magically reappearing? Well, this is where the second point comes into effect. The signal would need to be band limited. This means that an input signal going into the conversion process is stripped of all frequency components above the maximum of 1 Hz, and the digital signal, once reconverted, is again stripped of all frequency components higher than the maximum of 1 Hz. This can be accomplished by using a low-pass filter. A theoretical low-pass filter would only allow the passage of frequencies lower than a set threshold, and would block all frequencies higher than the threshold. I mentioned a theoretical low-pass filter here, since practical filters can't simply cut off abruptly at a certain frequency, but rather ramp down smoothly. More about this later. But let's now look at a more audible example. I'm going to use Audacity to demonstrate some of the examples here. If you haven't heard of Audacity before, it's a free and open source digital audio editor, and you can download it from the link below. I'm going to change the project sample rate to a low value. I'm going to choose 8000 as the sample rate. So according to the sampling theorem, we have learned that we can only hope to represent frequencies below half that rate. We can represent frequencies till 4000 Hz and no more than that. Let's try to generate a sine wave, and we'll go to generate and tone, and we can choose a frequency here. You can see that Audacity will not let me generate a tone higher than 4000 Hz. We'll bypass this failsafe later and see what would happen if we were to choose a frequency over half the sampling rate. But for now, we'll choose something more sensible. Say 1 kHz. Well, it sounds like a 1 kHz signal. We can quickly select a bit of the audio signal, go to Analyze, and plot spectrum, and we can indeed see that it represents a 1 kHz pure tone. I'll admit, this is a bit of a cheat, because we're not generating an analog 1 kHz signal and digitizing it, but rather building the sine wave in the digital domain and then sampling it. But it's fair to assume that the end product is the same. And without having a physical analog signal generator sitting beside me at this moment, this will do fine. Now let's explore the fringe of possible frequencies. 4000 Hz, exactly half the sampling rate. Audacity lets us do this, but where's the signal? You can play it and you can plot it, but the signal is nulled out. Nothing exists. This is easy to illustrate. Let's take a 4 kHz signal and only sample it twice a cycle. This is the current situation. All sampled points, unfortunately, sit at the zero valued point of the signal. So naturally, this is interpreted as no signal at all. But increase the phase offset of the signal by just a bit, and suddenly the wave comes to life. So this is the reason why the sampling theorem states that all frequencies lower than half the sampling rate can be represented accurately, and doesn't say anything about exactly half the sample rate, because it wouldn't be an accurate representation for all scenarios. So what about 3999 Hz? That's lower than half the sampling rate, right? Let's find out. In Audacity, we'll generate a sine tone of 3999 Hz. You get this bizarre output where the amplitude is modulating from high to low and back constantly. Surely enough, you can hear the 3999 Hz signal, and the frequency plots say so as well, except for the fact that the amplitude is all messed up. I'll try to explain this in a little while, but let's push on and push up the sampling rate. We need to create a new project in Audacity because you shouldn't have audio signals of different sample rates in the same project. In this project, we'll select our sampling rate to be the next available value of 11,025 Hz. and will produce the same 3999 Hz signal. This signal is comfortably below half the sample rate, and it's reproduced quite well. No weird modulation. The plot shows the correct frequency as well. Now let's zoom in. Yeesh, that looks pretty bad. And in no way does that look like a sine wave, or even a periodic function for that matter. But the strange part is that it's generating a pure sinusoidal tone of 3999 Hz. Let's repeat this exercise for a sample rate of 44,100 Hz. Generate the same tone and zoom in. That looks more representable, has better resolution because of more data points, but it produces the same tone. No perceptible change whatsoever. What advantage do we have then when changing the sample rate from 11,025 to 44,100 Hz? We got more data points, but no general increase in quality. Of course, with a sample rate of 44,100 Hz, you can represent more frequencies than is possible with a sample rate of 11,025 Hz. But for the specific frequency of 3,999 Hz, it offers no advantage. I'll repeat the same exercise for much higher sampling rates, first at 96,000 Hz, and then at the preposterously high 192,000 Hz. And I'll lay them all together so you can hear the difference for yourself. Convinced yet that there's no difference? Audibly, there is no difference. But viewing the waveform, it's dodgy, alright? Now let's explore why this is the case. For one thing, we've been viewing the waveform all wrong. We don't just linearly interpolate between two data points and put a straight line between them. This is an inaccurate representation. Let's fix that. We're back in the project with 11,025 Hz as the sample rate. We'll go to Edit, Preferences, Tracks, and then we'll change the display samples to stem plot. Much better, because this is exactly what we have in the digital domain, discrete data points and nothing else. Now, when the time arrives when this digital signal needs to be converted into an analog signal for us to listen to, it goes through a series of electronic circuits. In the simplest case, it goes through a resistor ladder circuit. And without unnecessarily complicating this video, it produces a stair-step pattern of an intermediate analog signal. So our data points are turned into an analog signal, which looks like this. This isn't the final output signal yet. In this form, the analog signal has a lot of super high frequency components. Some would even be ultrasonic frequency components, which we can't even hear. How would you tell this? Well, it's not clearly evident from the waveform what the exact frequencies are, but whenever a time domain signal shifts almost instantaneously like this, it means that the cone of the speaker would have to resonate and vibrate according to the signal, and move its cone really, really fast. When events like this occur once in a while, it's usually perceived as clicks and noise. But if it tends to repeat periodically, you're likely to get a high frequency tone. And the frequency would depend on the slope and height of such shifts. In a complex real-world input signal, you would end up getting a complex spectrum of high-frequency components in the intermediate signal. The obvious thing to do would be to cut off these excess frequencies and discard them. And the most obvious place to start would be all the frequencies above half the sample rate, from which point on will be referred to as the Nyquist frequency. This is because we promised that the input signal would be band limited when it first arrived at the analog to digital conversion stage, by putting a low-pass filter on it with a cutoff as the Nyquist frequency. Clearly, the output signal would need to adhere to the same rules and the same low-pass cutoff at the Nyquist frequency as well. And when the filter is applied, the intermediate signal is transformed into this, which is essentially a smoothed out version, which intersects all the points that were previously sampled. And this is where things get interesting. The signal produced that goes through all these points is a mathematically unique solution. There can only be one band-limited signal that can pass through all these points, and it is the input signal itself. So the input signal passed through the analog to digital conversion step is the only possible signal that can be produced at the output stage of the digital to analog conversion. If the output signal were to deviate even slightly from the input signal, it means that it would have to contain frequencies higher than the Nyquist frequency, and it would fail to meet the criteria put forth by the sampling theorem about band limiting. The conversion is mathematically lossless. Of course, analog components are never noise-free, and the whole process would add a little bit of noise into the signal, but if the conversions are kept to a minimum, it's never noise that can be heard by our ears. It would be stellar to see and hear the intermediate signal with all its high-frequency noise, but it's not possible because the filter right after it is baked into the DAC circuit, and you don't have an off switch to switch off the filtering. But what you can see is the output analog waveform. I can't demonstrate this to you because anything visual that I can reproduce on my computer screen is still well within the digital format, and you need specialist analog equipment to view any analog waveforms. I, unfortunately, don't have an analog oscilloscope lying around my house. But I can redirect you to this excellent video demonstration by Monty from ziff.org, where he introduces a full signal path that you can view, which can help you solidify the concepts that I'm putting forth here. The video is in the description below. Do you remember that I mentioned that the low-pass filters cannot cut off frequencies exactly at the Nyquist, but would require a smooth ramp? For this reason, we need a bit of a buffer between the highest frequency that we want to represent and the Nyquist frequency we need to completely cut off at. This gives us a clue about what could have gone wrong with the 8 kHz sampling of the 3999 signal that was amplitude modulating. Let's imagine the cutoff frequency implemented by Audacity is at 4 kHz or the Nyquist frequency. The practical limitations would not allow it to simply cut off all frequencies above that, and there will be some spillover. We know that there will be extra high frequency content because the intermediate signal will look like this. There will be a gradual reduction of the frequency content above the Nyquist, but they'll still be there. This is in direct violation with the sampling theorem, which requires there to be no frequencies above the Nyquist. But what happens when there is? We get the folding of the high frequencies at and above the Nyquist back into the original spectrum due to a phenomenon called aliasing. Clearly, aliasing puts additional frequencies into the output signal which didn't previously exist to begin with, and this is a bad thing, and we want to avoid aliasing artifacts. These extra closely represented high-frequency signals folded back onto the original signal is what causes the interfering amplitude changes. Let me demonstrate this. Let's go back to Audacity and select a new project with a pretty high sampling rate. Let's generate two sine tones. One is 400 Hz and the other is 401 Hz. The difference between the two signals is 1 Hz. Now let's select both the tracks, head on over to Tracks, Mix, and then Mix and Render to a new track. What we can see here is an acoustical phenomenon called beating. It's an interference pattern between two sounds of slightly different frequencies perceived as a periodic variation in volume. More about this in a module on acoustics. But this is essentially what's happening in our example, with aliasing ruining our output signal. So it's well worth it to have a bit of a buffer between the highest frequency we want to represent and the Nyquist frequency above which no frequencies should exist. This is why the beating effect and any aliasing vanished when we try to represent the 3999 Hz signal on the next higher sampling rate of 11,025 Hz. This meant that there was a considerable buffer between the highest frequency content that we wanted to represent, which is 3999 Hz, and the Nyquist frequency, which is half the sampling rate at 5512.5 Hz. So for all practical intents and purposes, we want to modify the sampling theorem to suggest that instead of sampling at 2 times the highest representable frequency, we want to increase that to 2.5 times the highest representable frequency, commonly called the engineering Nyquist theorem. This is done not because of the mathematical limitations, but practical electronic limitations. I think this is a good time to step off from this video before it becomes any longer. But we've barely scratched the surface here. We haven't even talked about sampling actual audio here. We've only looked at sampling control signals. But this is a good start theoretically, because it enables you to make informed decisions when choosing sample rates for your project. In the next video, we'll look at some of the more commonly used sample rates for audio processing and for representing high-fidelity audio. We'll study the advantages and drawbacks associated with these sample rates. We'll look at choosing a sample rate for a specific situation or application. We can check out hearing tests to solidify our concepts, and we can explore what aliasing sounds like and eliminate it for good. See you in the next one.